Okay.
Well, good afternoon, everyone. It's great to have you again with us. My name is Nikola Bešinović. I'm from Delft University of Technology. It's my pleasure to start this first year RAS webinar with Dr. Trefor Williams. He's currently in Vermont, but has ample experience in academia and consulting in the areas of railroad engineering and construction management. So he is Professor Emeritus of Civil Engineering from Rutgers University. Basically, how we'll go today. We have 1 hour, and presentation by Professor Williams will be about 45 minutes. So all the questions that you may possibly have, feel free to write down in the chat, and we'll bring them up at the end. You can do that during the presentation as well. And the recording and the slides will be available after the lecture. So I give the floor to Professor Williams to give us this interesting overview on this super popular topic on deep learning and text mining in railways. Please, floor is yours.
Thank you very much. It's very nice to be here this morning, and thanks for joining me. Just let me say before I start that I do have some actual railroad experience. I worked for a Class 1 railroad for a couple of years, the Delaware and Hudson Railroad, which is now been taken over by other bigger railroads, but also, my father worked for the Delaware and Hudson in management for about 50 years, so I spent much of my childhood in railroad yard offices and places like that. So, and also, most of my research previously had been in construction management, and it's just about the last 6 years I decided, well, I was always interested in railroads, and I had gotten interested in AI, so I said, let me see what we could do with some railroad data. So let's see here. All right, so the topics. I'm going to talk about text mining first, which I became interested in, and then my sources, and then we did a thing called topic modeling, and applied it to various railroad data. And there's two examples. One is accident reports we mined, and the other is trying to find locations with frequent maintenance activities. The second thing is then went further with the text mining in that there's been some really interesting advances in deep learning the past few years. And so I'm going to give two examples of deep learning. When I say introduction to deep learning, I'll just touch on the basics. Some of the models are extremely complex, but the thing that's nice is that there's a lot of stuff available open source, and that even a civil engineer like myself who's not a programmer, you can use some of the different things. So I give a couple examples of predicting switching performance, knowing the maintenance activities that are going on. And then also something that's really fascinating is that now there's this capability, there's a new types of deep learning networks called transformer networks, where you could even do things like question answering from manuals and things like that. And it's very really interesting. Even well, as we'll say, Elon Musk is in on that. Let's see. Well, yes, we'll talk about how you could combine both text and numerical. And I'll just give you at the end some ideas about future work. So anyways, let me start out. If you're not familiar with text mining, is that we want to take unstructured text and be able to use it in some meaningful way. And certainly there's the possibility that text that we have has got some meaningful patterns in it. That might not be obvious. And of course, the other thing with some of the textual databases of railroad data, like the Federal Railroad Administration of the United States, there's so many accidents reported, and it has a text field. No one may ever, actually read every single one. And then, of course, there's so many, it'd be hard to draw a conclusion from it. Well, with the text mining, you can do that. So IBM, and hopefully you get better decisions. IBM tells us that 80% of the world's data resides in unstructured formats like text. That you can get a lot out of it. And of course, also now all these various things. If you go to IBM's website, they have their, I believe it's Watson, which you can pay for. It's got all the various text mining techniques built into it. And lots of things have text mining. I wrote a lot of my programs in MATLAB that has text mining functions built into it now. Didn't used to. But it's a big area. So I use topic modeling. So topic modeling is where we're going to have a lot of text documents, and this algorithm that we used, it is going to find the major topics in the text, and it's going to identify the major words in each topic. So I'll give you my first example, is that we looked at accident reports. The National Transportation Safety Board is a US agency. It essentially investigates accidents with injuries and fatalities on railroads. The FRA accident database, it's actually the equipment accident database. You can get that online through their webpage, but it's every railroad accident greater than $10,000, or it's more than that now, maybe like 15. But it essentially is all, $10,000. That's pretty easy number to reach these days. So it includes most accidents. And that is a database with all sorts of categorical fields. But what we mined was they do have a text field in their database where you can put in free-form text, which describes the accident. And then finally, we looked at the rail accident investigation reports from the UK. And I spent a year in the UK at Cardiff University. And I think we'll find when we see this is that they used to make the joke that the United States and the UK are two countries separated only by a common language. So that's joke number one for the morning. All right, let's do topic modeling. All right, so we looked at accident reports. This is from Japan, but and topic modeling is possible with Japanese or Chinese text, no problem. All right, so one of the big things also that we use some of these various modeling techniques is that it needs text as the input, but it turns out that it's no problem to convert PDFs, which the accident reports were, or data from Excel spreadsheets to text. And one of the things there is pre-processing involved with text, and like stop words are words like the and I guess of, common words. So so then these very common words, if you use them in the model, they would distort it because they occur so often. So you remove that, you remove punctuation, and then you have to do this thing where the text is tokenized into its individual, basically individual words. But, and there's lots of things you can do with that. One of the things is that, of course, people misspell things. And if you have a lot of money and time and people, well, you can go through and before you do the topic modeling, you could correct the spelling mistakes and things like that. But we didn't do that. All right, so the model, the exact topic model that we used was called latent Dirichlet allocation. The mathematicians tell me that Dirichlet is a distribution. It's not someone's name. And the big reference for that is one of the people who developed this model. His name is Bly, and it's a really good kind of a general article in the communications of the ACM that's available. You can get that online. And also everybody really includes, it's not a hard thing to get at in that MATLAB includes it, statistical packages. I use JMP because I have a Macintosh. That is the Macintosh version of the SAS statistical package. So that is built into that. So you can do LDA with that. And also there's these various machine learning frameworks that you can get, like RapidMiner or NIME, which is free. A university in Germany puts it out, but with that also you can do that quite easily without programming. So the outputs we're going to get, we're going to take, right now we're doing the accident reports. We're going to take the accidents and reports and get ranked topics from them. And we're going to know the probability. The other thing that we get from it is then for the topics we get, we will also know for all of our accident reports what topic the algorithm places it in, or the most likely. It's all probabilities. All right, so this is the input, as I said about the mistakes. This is from the FRA. This is just the text, free-form text field. And you see that's just a few sentences. It goes from about a few words to a couple of paragraphs. This would be typical of some accidents. There's thousands in the database. You can go back 10 or 15 years. All right, so now this is what you get from the LDA. This is MATLAB output. And so this is the FRA equipment accidents. And you can see that these are the major topics. All right, there's, let me just say one. Okay, topic 9, which is the bottom left topic. If you look at that, right, that says bowl, hump. So one of the topics, it's found from all the railroad accidents the FRA has collected that hump yard operations, there's a lot of accidents. The other one is topic 10, which is the bottom right-hand one. One thing that's interesting, if you do anything with the text of grade crossing accidents in the United States, you will find that tractor trailers get mentioned. And it comes up very frequently, trucks, trailers, driver, you see. So that the primary, so a big thing, big trucks getting hit, getting in accidents with trains at grade crossings comes up. And there's some other things. I'll tell you the most frequent, we plotted out the most frequent, which topics occurred most frequently. It's switching. Both topic 1 and topic 2 concern switching. Let's see. Yes, see, topic 2 rolls. Broken broken wheels, switch points was the third topic. But then finally, then number 10, the grade crossings is the fourth most frequent accident. So that's the United States, and that's just kind of the general accident database. Now, if we look at NTSB reports, these are the reports when there's a real serious accident, say with fatalities. This government agency comes out and investigates the accident, and different things come up more. Naturally, Amtrak runs the passenger trains in the United States. And so if there's a bad accident on Amtrak, that's a topic. That's topic 3. They also do transit, mass transit accidents. That's basically topic 4. People, is that topic 5, red signals. Topic 7 is grade crossing. Okay, so that's good. And again, most frequent one was switching. Topic 1, workers on tracks is a problem. And remember that because we're going to look at the British next. All right. But then remember, this is a different database in the FRA in that it's the bad accidents, injuries, fatalities. All right, now this is the British LDA topics. I made the joke about separated only by a common language, as I was told when I was at Cardiff, is that, of course, the number 1 accident in the British is the level crossing, which is, we call it a grade crossing. Probably everybody knows that. So, and the other one that I think is going away, but also is a topic in Great Britain that you don't get in the United States, is there's accidents, the word doors comes up. That was kind of frequent, unusual that I went back, I got going back to it's like the 70s, every single accident report, right? And so the British railway equipment has changed, but if you'll remember, if you go back 30 years ago, unlike the United States, if you're a passenger on the British train, you open the door. You can get off yourself, right? So they've had accidents, in stations where people open the door too soon, things like that. So that showed up, but I think that's going away. The other thing that's kind of interesting, of course, is the topic 5, and we said workers on the track. In Great Britain, right, they have some reasonably high-speed passenger lines, but also they have the operating companies and a separate company that does the maintenance. And if you look at that, there seems to be, there's a couple accidents with workers on the line. And if you go back and look at the text of these accidents from this group, you'll see that sometimes there's coordination issues between, let's say, the train dispatcher and the crews about, the track being available, things like that. But I don't mean to pick on the British. They have very good safety. Okay, and see again, the British, this level crossing is by far the most frequent that they report on. And so just by chance, I learned, and I saw this came up independently. I went, and if you look at this, you'll see that it involves level crossings. You see footpath in topic 1 is a pretty big word. So I went over, there, and someone told me a story that they have some pretty high-speed lines. There's a lot of people love to hike there, a lot of footpaths crossing some high-speed lines. And so we went back and did a more basic type of word processing, not word processing, text mining, where we said, what's the most frequent word pairs? And again, of course, level crossing, grade crossing accidents, but this footpath crossing is prominent. And that's because someone took me to a place and showed me this. This is 125 kilometers per hour. And there's a sign. And, these have these place, you can cross, but it is, and this place was on a curve, and it turns out they do have some problems with people being hit on lines where the speeds are fairly high. Okay, now this one I think is maybe more of more interest in the sense that we worked with a short line, and I signed a non-disclosure agreement. So I'll tell you a little about this short line. Is that it's kind of unusual in that this railroad, it has a large hump yard, large classification yard. And also it has through freights that operate on the short line to and from the hump yard. If you're from the United States, you could probably figure this out. But so it has sort of character, it is classified as a short line, but it's a heavy duty railroad. All right, so they had, we were able to get from them, they have a daily maintenance log where they describe their maintenance activities for the day. Sadly, we first thought, well, we'll put this on a GIS map, right? Because surely they give us the milepost or the latitude, longitude, and they don't. But it did include location names. So let's see where their accidents. So we have locations, and we have the type of maintenance in the topics. Now, we had to hide the names. I had to change all the names. But Yard A is their hump yard. So obviously they do a lot of their maintenance work there. The main line, which is topic 8. There's welding topics. Switch maintenance is a topic. And there's are some locations get picked up. But originally, I say I do have this kind of old railroad background. I was thinking, could you use this and you could find some place where maybe there's a problem, bad drainage, pumping joint kind of thing, and you're always going out there. But possibly, but again, it would be really nice to have been able to link this to some kind of really specific location data. All right. So that's an introduction. That was the first kind of crack at text mining. I thought there's some possibilities there. And then in working with some various things. Well, I'll give you background. I worked starting back when neural networks kind of first came out, back in the like a million years, no, not a million, 30, 40 years ago, 30 years ago. Worked with neural networks. I was interested in construction management then, and I got the idea you could try to predict the cost of a project from information you had at the time of bidding. And I did a lot of work with that. And the thing is, there was a trouble at the time, right? Is that a neural network, right? We're going to put our training data in. And in that initial example I did, that was the historical information about the project, what the low bid was and how many bidders and what type of project it was as input. And then the output would be a prediction like, couldn't do a whole number, but you could do things like this project is going to have a high cost overrun or a medium cost overrun or a low cost overrun based on this historical training that it's had. But the original neural networks, they were limited by the computing power also into 3 layers. All right. Also, if you're not familiar with neural networks, this is kind of a biological analogy in that this is how billions of cells in your brain are arranged in this kind of parallel way. And basically your brain is, it can be like zero. It can be like 0 or 1. And also there's an activation function where your neuron in your brain fires and goes on to the next neuron and things happen. So again, this is another old, not old time, they still use them, but three-layer network perceptrons, they were called. And one of the things you need to know is that the learning in the neural network is embodied in these weights between the layers. Gradually, the network learns the appropriate weight that makes the best prediction. So not to get bogged down with that, and there's tons of books and stuff written about neural networks. And this is one of the original ones. Okay, now the trouble with neural networks, really, I should have added a second thing, but I'll tell you both. That I found is that it's a black box, right? In the sense that you put the input in, it's not like some computer program you wrote where you're telling it, figure this out. It's just learned. You don't have any control over how it's learning. And so it's possible you don't really know how it arrived at the answers. In the original neural networks, you couldn't look in and see the weights and see how it arrived at the answer. So coupled with the fact that these networks need a lot of data to train, people made some mistakes with these earlier neural networks. And I can give you an example. There was a US government agency that I worked with related to flood control, where they thought they could do a neural network and they had 14 examples, right, of flooding on a river. That's not enough, right? Because there's certainly more than 14 different situations where there's flooding. And so the thing will give you an answer for any data you put in. But if it hasn't been trained on that particular situation previously, it won't give you a very good answer. Now, a lot of neural networks they use, and now they use millions and millions. You don't necessarily need this for railroad applications, but they have these things where they want to train these neural networks to answer questions from posts people made on Facebook. They use millions and millions of posts as the training data. So you have to have enough data. And you have to be able to live with the fact that in these original ones, you really didn't have any idea where the answers came from, where the answer. All right, so that's 30 years ago. And neural networks kind of died out a little bit. They're always out there. And they were good for some problems. But then the development was the computers got incredibly faster. And they went to deep networks, which are much more accurate. And that is that hidden layer, rather than one hidden layer, you can have many hidden layers. And they found, and the other thing is they've developed now ways where the answers you do get are explainable. The downside to it is that these networks are very complex, hard to explain. I said I was going to explain it, and then I looked and, I don't want to turn this into a computer science, and some of it I don't even understand, very complex mathematics, but that doesn't mean you can't use it. So we're going to start out with a recurrent example of a recurrent network. Oh, I'm sorry. These are things they do. That original network I showed you, that's feed forward. It goes in one direction. You put the input in and the different algorithm works and gives you an answer, and things are only going in one direction. Now the recurrent is that there's feedback loops in these networks. The other thing now, they actually have memory built into them now, in that before it was they just worked on the particular example you gave it. Now they can remember previous examples as well while it's processing the present example. And it gets very complex. And in fact, I'll give you an example where people don't really know how it did it. And that's the thing. If you're going to do this, you're going to have to work on it, apply it to a railroad. You're going to have to really test it and use it to make sure that you're just getting answers that make sense or are appropriate. All right, so the first thing I did, LSTM, that's implemented in MATLAB. And I'm coming back to my short line, who was kind enough to give me the data. And I said, Well, I want to use long short-term memory networks. And so these are deep layers. They have many nodes in each layer. And they're not just dealing with single tokenized words. They can handle sequences of words and handle that there is obviously, if you have a sentence, there's dependencies between the words. So it can learn these long-term dependencies so that you can bring new text to it. The one thing you have to do is also was an advancement, these maybe the past, I think it's 10 or 20 years, is that neural networks, they don't want to work with text. So you have to have some mechanism to convert the text to numerical vectors. And there's programs are developed called to do word embedding, which converts the text to a vector of numbers. And they're pretty complicated too. But I use MATLAB, right? MATLAB does it, built-in function. MATLAB has a text mining toolbox. All right, so I'm going to link, our short line is going to link the maintenance activities to operations. And I took that picture. I said, gee, I know a little about railroad track, but I don't know, what would you do with that? Is that got to come out or is that okay? So we're back to our short line. So we tried to pair, they gave us some operational data. And this is only an example. I think these examples I'm giving, I think it's just to show, I'm not saying this is something you necessarily ready to go out and use on a railroad or even useful for a railroad. But the point is that if you have lots of data and people in the railroad industry keep telling me that the class 1 railroads in the United States have all sorts of data, well, I'm just suggesting possibilities that if you have text, that you can use it. Okay, so we had the daily maintenance activities, and we knew the switching misses, that which freight cars were not delivered on time. So he said, well, let's use a neural network. Can we predict the effect of heavy maintenance or of maintenance activities on the switching misses? Okay, so to train the neural network, we had some data, it's about 4 years worth of these maintenance logs. It's just text in an Excel spreadsheet. So you have to split it into a training and a testing set. And then also the output. When you train it, you have to couple your input text with the appropriate output. So we said, we found we couldn't just predict a number of misses. That was too difficult a task for the data we had. So we did low, medium, and high switching misses. Same with my text prediction, my cost prediction way back when. And so we applied it to an advanced neural network model, the LSTM. And then once it's trained, you can give it new input and it makes a prediction of what the level of switching misses will be. Right. So it's mixed results. Maybe we didn't have enough data. Maybe it's too hard a problem. Certainly there was days when the text was, only a few words of the maintenance activities. But anyways, we got it with this predicted 3. We got about 55% accuracy, which if you think about it, totally random, if you're trying to find 3, we're just making picks, you'd be like 33%, right? So there's something in there, right? And that in fact, the high levels of switching misses, obviously there's a connection between them and the heavy maintenance. Like in particular, the short line told us that surfacing and activities where tracks have to be taken out of service, obviously, yes, they have a big effect. Okay. and that there's some patterns there. So anyways, this is a confusion matrix, which is the output of a lot of different neural networks, is that if we were 100% correct on all of our predictions, everything would be on the diagonal. So blue is good, and bluer the better. So anyways, for each class, we're able to predict, in particular for the high level of switching misses, we're able to predict about, what did I say that was, 67%. We got two-thirds correct, right? The true class, we got 16 correct, and then we had eight wrong. And so I thought that was kind of interesting. And the other ones, the biggest number was on the diagonal, which is interesting, I think. But you know, this is not something that necessarily could use, but if you have better data, and the other thing with neural networks, don't forget, you can always combine it with other numerical data that you have. And I've done this in the past, but this data, the railroad data I have, it wasn't quite appropriate for it. So these things are out there. And if you compared it, if you went back and just used the original 3-layer networks, they perform much worse. So there's something out there, and if you have a lot of data and you can formulate a good problem, you can do something with these. And also don't forget that if you have numeric data that you could combine with your text data, then you could do even more powerful things. But the data I had was limited. But I just thought I would try these things just to suggest. Now, the final thing I'm going to talk about is the transformer network. And this really floored me. I came upon this on randomly. Just surfing the internet, and I said, well, again, I said, I'm not a computer programmer, I'm a civil engineer. There's no way in the world I could ever do this. But it turned out that there was. This is a new thing, 5-10 years. It's a family of neural network architectures. It's based on this idea of self-attention. All right, and then if you just search on the internet for attention is all you need, this paper is everywhere. You can get a copy of it, of where these computer science people describe what they do. It's quite complex. But anyways, is that it deals very well with the relationship between words. So, I mean, if you put in a paragraph of text, not only is it dealing with the individual words, like we started out with topic modeling, now it's dealing with the sequence of words. Now, the other thing that was kind of, I want to mention this OpenAI, before we go on, just so you know. First, you can see how this arrives at decisions. You're able to look at the weights. So that makes people feel a lot better. It makes me feel a lot better. The second thing is, though, there's been a little problem. I mentioned OpenAI, and this is the one that Elon Musk is backing, and it's very remarkable in that it can do these things like question answering. And that's the example I'm going to show you, but I'll use a different algorithm. But here's the trouble. It turns out these things, you got to train them on like an enormous corpus of language. So it turned out that this one they backed is GPT models. They're on the GPT-3 now, and some of it is open source, some of it you have to pay for, but with OpenAI. But they trained it on like every, I'm not quite sure how it goes, but like every like Facebook post there ever was. So what's the trouble with Facebook posts? It has bias in it, has bad language in it. You know, the whole thing. So the trouble was they trained these things and it was very remarkable, except every now and then it would spit out some awful thing, you know, have bad words in it, racist things in it, bad. So they're working on that, but I think it had more to do with what it was trained on. Because I use this for my railroad example. I said, let's try question answering from track design specifications. This is a little sidetrack near where I live. And I use this one, BERT transformer models. And I said, I don't know, I'd be interested in trying this out. But it turns out that this BERT, it's been trained basically on from places where there was good language and not so much bias. It was trained off like Wikipedia and that sort of thing. And that is also the amazing thing that you can use these things in that it takes a supercomputer to train the network, but you don't have to do it with your computers. The trained networks are up there and they're open source and you can just get them. And if you look, there's a strange word, hugging face down there in that last bullet point. And of course you can also go to Google, but Hugging Face is an open source repository of all these different transformer models. And on top of having the trained model that you can download, they give you the Python source code available to use it for different types of models. So I took their source code. First of all, when I was fascinated by this, I didn't even know any Python. So my trouble was I had to learn enough Python to be able to download these Hugging Face trained model and then also run a little Python program that would solve my problem. So here it is. The limitation I had was that, you know, I'd love to put like a whole design manual, the federal track standards in there, something like that. But anyways, I found there's a few pages. You were limited to a certain number of characters. I think 500 characters for what this would do. So I took a portion. BNSF has sidetrack standards, and they're all over. They're on the internet. So I downloaded it, and this is my sole input to my transformer model. And so I also input the questions. So what's the maximum allowable curvature on an industrial track? And if you see, we go back, it's 9 degrees, 30 minutes. So I input, you input the text, you input the questions, out pops the answer. And got them both right. And I didn't do any program, I didn't do anything other than put that text in and formulate the questions. And I mean, to me, that's an incredibly powerful possibility. Of course, I've given you the caution that depending on what you train it on, you know, you could get some unforeseen and undesirable results, which is what happened with that GPT. But at the same time, they say that GPT gives remarkably good answers at the same time. So I always think, you know, I always liked mobile computers. I don't know, but isn't there the possibility that you could have a laptop or something, and that if somebody has a question, you know, you have this on the laptop and it answers the questions about, say, track standards or design manual. The other thing that's exciting is that these transformers are better at image recognition than some of the previous neural network models. So now you start talking about what, could you take a picture of a track flaw and then have it generate, I don't know, appropriate I guess my question was, if I go back to this picture, I don't know, can I take a picture like that and it's going to tell me like whether I should replace the rail or not, depending on, what kind of track, track class it is. I could see my eye falls on the fact that there doesn't seem to be much ballast there in that track, Well, that's an easy one. Anybody could get that. But I mean, little more subtle kind of things. So, I mean, is that rail worn out or not? Okay. All right. So it looks like this is Princeton Junction, New Jersey. There's an Amtrak train going by. I still live down there. It's possible to extract meaning from the text databases. And it looks like it is. And when one other thing when you deal with railroad people and the track thing, some of them have been out there for many, many years. And I think that the thing is that you want to find databases where you can get some meaningful stuff that people just don't know, obviously, right? Like we looked at that previous picture. Yeah, that needed more ballast. I think that this transformer networks, it looked like the future. I mean, it's the computer science people. It's red hot right now. I wish I knew more about computer science. But also I think the techniques, these are just some toy examples I worked up, but I think it apply to all sorts of problems. If you have data, you can think about using these neural networks. And also remember that you can use these neural networks. I emphasize text here today. You can use it with numeric data. I mean, certainly if you read the railroad trade journals, everybody's trying to work on taking the data from track telemetry cars and trying to do something with that. And certainly these networks are getting very powerful, and probably they would be ideal to try to develop applications in that area. And so I think that's about all I had today. I hope you found it interesting. Any questions?
Yeah, okay. Well, thank you so much for this pretty interesting conversation. And actually, you touched upon quite a lot of meaningful and hot topics. And during your presentation, there was a pretty fruitful discussion going on in the chat. So I prepared a few questions already. So
sure.
So we can start with one from Thomas Graffanino. He was asking about the experiences to adapt the models due to English versus American, British English versus American English. So there are different keywords being used. So how did that impact your models?
I see that question. I'm not aware of any models that say are. Well, actually, that's not true. For the transformer models, they have specific ones for the different types of English. Whether it be American or Canadian or English. Is that what the question is about? Yeah. Now, I didn't do any of that.
Data. Yeah. So you looked at different data from Great Britain and the US. So
correct.
Did you make some adjustments for these differences?
No, I didn't. I mean, it would be nice to do that. Now, I did all this basically unfunded, and it would take a very long time to do that. But if you had funding, I think you could, clean it up and convert, like say you could convert level crossing to grade crossing. And then, then say that, and then the two, that would make the outputs more comparable, I think. But, I haven't really had the time to do that. I think it's a really good suggestion. And there may, in fact, be automatic ways to do it. It is if you search the web and then some of this computer science stuff, and then you come back in a month, there's something new. So when I started out, you couldn't convert PDFs very easily to text. Now, every program you get, it's no problem.
Yes, okay. And speaking of your second topic again, when you talked about three types of high, medium, low labels. So
yes,
the question was, how do you split labels into three types? Was it done manually or?
No. With an Excel spreadsheet, I knew for each day, I knew the number of misses. And so then just with Excel, you could make that, turn the number of misses into high, medium, or low.
Okay, so indeed the follow-up was what is the prediction horizon? But if I understood well, you predict for 1 day.
Okay, 1 day at this point, and which was limited by the available data. So the thing that's you could do a longer horizon if you had the right data. In fact, now that you say that, that would have been a good thing to do. Maybe try, but we really didn't have enough data to do that. But you very possibly could. And then if there was a relationship in the data, the neural network would find it. My idea that I told this railroad, and they had different priorities, and again, this particular application may not have been something that they would help them very much. But I said, well, why don't you generate the night before you do this maintenance work? Why don't you generate a list of what you're going to do the next day and put that into the neural network? And then you could have a prediction of possible impacts on that day. Like, have you lined up a bunch of maintenance that's going to have a big impact? And then you could go on, is there some way you could shuffle that around? And but we are limited to 1 day at this point.
Okay, thanks. And we have a question from Warren Powell. It's about data labeling. So it says basically that it's indeed true that we need large training data sets, but how large it actually have to be? So is it really large? And do we need labeled, or do we have labeled data, or who would be doing labeling? Is it still a human work, or we could have it automatized?
Well, from my reading of kind of the current state of the art is that some things still do need a human labeling. Now, the way I formulated my problem was that I was able to merge two different sets of data, so that I already had the output in the number of misses, and I could easily convert that to the categorical value using Excel. So I never had to put the labels in. But I've read in natural language processing papers where people did extensive human intervention pre-labeling. So the answer is that I guess both, that some things you might have to do that, and then other things, if you have some data, two separate sets of data that you can merge together and one to be the output, then you don't. The other thing you mentioned, that the number of training cases, people give various answers to that from computer science. The one thing is that they say, well, your training cases should cover all possible things that could happen. And so that probably means you need quite a bit of data. Now, if you look at MATLAB's documentation, they do some interesting things. I think it's medical related, where they have like 500 training sets. But then you'll read these things about people, these companies trying to do automatic question answering from input people give on Facebook. You know, they want millions to train it. So I think the answer, it kind of depends on your problem. And the other thing you have to do is you have to do a lot of experimentation to see if you're getting anything reasonable. If you don't have enough data, you'll see that your output is not reasonable more often than not. But if you have enough, then it's makes more sense. But again, that was the original drawback of the neural networks, is that people didn't like it because sometimes they didn't know what was going on, and you're asking to trust an answer, whereas there wasn't really enough data used to train it.
Could I make a comment here?
Sure.
So I'm not an expert on neural networks, but I have written a book that I explain neural networks. And so I've gotten into the tools enough, and my lab did a fair amount. By the way, I'm going to have to thank you for the Norfolk Southern picture at the end. My lab worked with Norfolk Southern for 10 years. We built their optimization model for managing locomotives. And we used a technique called approximate dynamic programming, which the computer scientists would call reinforcement learning.
Sure.
And in that application, by the way, we never did use neural networks. But let me just, as a word of caution, let me take a simple example of predicting demand as a function of price. And let's say you want to fit a line. You need at least 2 data points because a line has 2 parameters. Neural networks are just big, complicated functions, big nonlinear functions. And they don't have 2 parameters or 10 parameters. They'll have 100,000 parameters. Now, when I learned statistics, and by the way, I'm also Professor Emeritus, Trefor, maybe a few years younger than you, but in my day, they used to teach us that when you have a noisy data set, you have to have about 10 observations per parameter. Now, I have been at conferences when people doing neural networks will just laugh and make a joke of the fact that they don't even have more data points than parameters, and they think it's okay. And I'm telling you, flat out, I don't think it's okay. But in your applications, in these labeling text-based applications, you do need a big data set. You don't have to have every combination. That's definitely not true. But you have to have a lot of them, and you have to have something on the order of the number of parameters in your neural network. Now, you can govern how big your neural network. You can say how many nodes per layer and how many layers, but the number of parameters is like the number of nodes per layer times the number of nodes per layer times the number of layers. Some of these neural networks are huge. The deep neural networks are huge. And this is a very specialized industrial application. I've got to feel like, wow, you need to have a data set where this text, and then here's the response. Here's somebody has to say, and here's what happened. By the way, it won't say what to do. That's a whole different problem class. The decision of what actions to take is a whole different playground. But simply classifying and saying with these words, here was the accident that happened. Gosh, that's going to take a lot of labeling. New York Times has a wonderful article that they did, and I took a screenshot where they talked about how these neural networks require a lot data, and then they went a lot of data, and they had a picture of a group of people in India, just huge rooms full of people typing in stuff. In the health arena, you'll have all these kind of people looking at breast x-rays and then saying, okay, does this have cancer, yes or no? And they build these huge data sets. You would have to have something comparable for this setting. So getting that labeled data set for a fairly specialized, complex problem like that, I think that's the challenge. I think that's the hurdle you have to get over.
I'd agree with that 100%. Certainly, anything I found that I've done work with the construction industry and now railroads, is that the data is just not out there for a lot of things. Anyways, and then you have to label it, but sometimes there's many things that you'd like to do, but you can't get your hands on it because it's trade secrets and all that kind of stuff. But yes, I know. I agree with you 100% that some of this labeling could be a real.
If I could also add, so I've retired and I'm helping my son start up in the trucking industry, and I've run into companies that specialize in taking. So in the world of all this high-tech computers and whatnot, there are still many, many, many small companies who do bills on paper, and there are still people faxing. So of course, companies have jumped into that with this technology, exactly the neural networks, saying, okay, let's take these paper invoices, scan them, use AI, use exactly the technology that Trevor's describing, and use it to help interpret it. Now, that would still require the large data sets, but it's out there, and companies are doing this and have been doing this for a number of years. So the whole use of neural networks for this text, I've seen people recommend utterly silly applications of neural networks. This is a good one. Text processing is a good one. And Trevor, I have a feeling one value, if we could get over this hurdle, is that probably a lot of people fill out these reports that nobody reads.
Yes.
So that's where you sort of yeah, the computer may not be perfect, but the alternative is where nobody even looks at the report.
Yes, that's correct. The topic modeling, thought, well, the FRA, they have that enormous database. Nobody ever reads that field. It just gets reported.
So Warren, you also illustrated the main danger of doing that too, right? So people who manually enter information in log files gradually come to understand whether those log files are reviewed in the future. And the quality of the entries reflects that. So as much as I like the sort of the initial direction, right, which is, to use all this human generated, contextual information or explanatory information about a situation. I prefer to point at machine generated stuff that is similarly unexamined, but is more faithfully and consistently rendered by whatever software application or hardware is generating the log.
Yeah, I agree. It's interesting how in today's day and age of computers, how much paper still moves around, or what I would call ugly text. So I don't know, maybe some of this is put on paper, maybe some of it is a human pounding away at a computer file, but Nicola doing exactly what you're saying. They know that nobody reads it. So it is somewhat astonishing. So with my helping my son with the trucking industry, there's more sophisticated companies who are very computer oriented. I think it is, after what are we, about 50 years since the invention of electronic data interchange, and there are still young companies that get started that think that moving to EDI is a big step up. We're talking about the 2020s here, and EDI, I think, was invented, I don't know, in the 1960s. It is a steady evolution. I've just become convinced paper's never going to go away. Trucking companies have more of a tendency to work with much smaller companies than railroads. Railroads are more typically working with bigger companies. Small truckload carriers can easily be working with a tiny mom and pop that haven't yet decided to put things on a computer.
Yeah, well,
And
if
moving to
you
a fax
allow
machine
me,
is a step up.
yeah, if you allow me for a quick interruption, I would like to formally close this discussion with just one remark to what you have been discussing the last minutes. What we could do as engineers and coming from the field could think of, instead of only asking about large amount of data, but actually putting a bit more direction of asking for some right data to be filled in. So maybe that could already help us in improving our models. And maybe we could ask even for less data. So that would be just a thought from my side. So I would like to thank again Trefor Williams for a great talk, and everyone for staying with us. Also overtime a bit. So the formal part is done, but if you are free and willing, Trefor Williams is more than happy to stay longer. So don't have to end the discussion abruptly. So we will stop the recording, but if you have more time, feel free to stay. Thank you once again, and have a great day.
Thank you.
Thank
Thanks,
you,
everybody.
Trefor.